Hi, I'm Arjun Singhvi, and today I'm going to describe a new approach to remote memory access suited for multi-tenant data centers. We have witnessed the rise of RDMA in data centers due to its low latency and high throughput benefits, as has been demonstrated in the context of key applications by prior work. However, when we at Google attempted to operationalize RDMA within our multi-tenant data centers, like many others, we encountered numerous deployment issues such as the connection-orientedness of popular RDMA transports leading to poor scalability ordering and failure semantics, the RDMA model not being amenable to support key security management operations such as rotating encryption keys, and RDMA not being amenable to rapid iteration due to key algorithms such as congestion control being baked in hardware. This led us to asking ourselves the following question. How do we design remote memory access for multi-tenant data centers, which resulted in 1RMA? Before going into the details of 1RMA, let us dissect why existing RDMA technologies fall short. Firstly, to overcome the scalability and performance issues of the connection-oriented RDMA transports, as noticed by several prior works, systems may attempt to multiplex independent workloads on the same connection. However, connection sharing leads to induced ordering as RDMA requires FIFO execution of ops within a single connection. Consider an example of large background ops sharing the connection with latency sensitive ops. As we can see, this can lead to priority inversion where the latency sensitive ops are stuck behind the background ones due to head of line blocking. Moreover, it imposes shared fate for independent ops sharing a connection. Moving on, we also find that RDMA today adopts a connection-centric security model wherein access control is tied to connections through protection domain, and thus it suffers from the connection pathologies that we discussed. Moreover, RDMA does not provide any ready means to manage encryption keys. For example, consider the following scenario in which a connection is established between the client and the server, and a golden encryption key is associated with the region being accessed. On changing this encryption key, there is a connection teardown due to authentication failure, leading to an inordinate period of unavailability as the connection needs to be set up again. Also, while Rekey enables RDMA traffic to coexist with other protocol traffic, it requires us to use PFC. However, as is well known, using PFC is untenable in commercial data centers due to its operational hazards such as poor failure isolation and deadlocks. Consequently, there have been many proposals to reduce reliance on PFC, many of which are deployed today. They either bake congestion response or more sophisticated loss recovery schemes in hardware. However, because they bake such schemes in hardware, they are not readily applicable in our environments in which such schemes are routinely updated and customized post-deployment. While RDMA suffers from several additional issues, details of which are there in the paper, we observe that RDMA is ill-suited due to its two basic design attributes, being connection-oriented and having complex policies baked in hardware. With 1RMA, our approach is to do a judicious division of labor between hardware and software, leading to a simple and fixed function NIC aided by software. Specifically, it leads to a fixed function NIC that operates on connection-free independent ops by means of explicitly finite hardware resources that are managed in software. This results in a simpler NIC design. Additionally, all transfers in 1RMA are solicited. Apart from this, 1RMA uses a novel software-driven hardware-assisted congestion control algorithm and a novel connection-free security protocol. It also provides first-class support for security management operations. Taken together, these ideas form the basis for remote memory access support in multi-tenant data centers. In the interest of time, I will not go into the details of the security protocol in this talk and would cover the remaining key ideas. Firstly, 1RMA is connection-free. The NIC acts on fixed-size ops and treats them independently. It provides fail-fast behavior in which the NIC tries to complete an op within a fixed time t. If successful, the NIC provides fine-grained measured delays to software, else it delivers precise failure notifications indicating why the op failed. In doing so, it leaves retry ordering and congestion control to software along with segmentation, as large application transfers need to be segmented into fixed-size ops which the NIC can service. 1RMA's division of responsibilities is in stark contrast to RDMA, wherein significant complexity is baked in hardware. On the other hand, 1RMA lifts some of the responsibilities to software, resulting in a simple fixed function NIC that is primarily responsible for op execution along with encryption and solicitation. Consequently, the NIC state does not grow with endpoint pairs, as is the case with RDMA. Secondly, 1RMA offers explicitly finite NIC resource pools. Unlike RDMA, the registered region table and the command slots are maintained in fixed-size on-NIC SRAM. This avoids the inherent complexity and performance limitations associated with cache-oriented RNIC designs, leading to simpler hardware and predictable performance. Importantly, having explicitly finite resources enables OneRMA to manage them in software and allocate the resources based on application business priorities, which is not possible with RDMA. Crucially, all transfers in OneRMA are solicited. That is, an op is not initiated by the NIC unless it is guaranteed to land its subsequent response data in the on-NIC SRAM known as the solicitation window. Once an op is written to a command slot, it is enqueued in an outgoing FIFO and it waits for capacity in the solicitation window. Once it reserves capacity, the op is signed and dispatched over the network. The solicitation window is sized based on the bandwidth delay product, and in this manner solicitation limits the severity of sudden incasts as it bounds the number of incoming bytes. Importantly, for a successful op, OneRMA provides fine-grained hardware delay measures in the form of issue delay and total delay. Issue delay indicates how long it took for the op to enter service, and total delay indicates how long it took to execute the op. And in case of every failed op, the NIC tells exactly why it failed. OneRMA uses these precise signals from hardware to implement congestion control in software. It uses delay as a congestion signal as it simplifies congestion control design. Importantly, OneRMA reacts separately to local and remote congestion by maintaining a congestion window for each remote destination direction pair and a single local congestion window, as local congestion affects all transfers. OneRMA modulates these congestion windows using a simple AIMD controller based on whether the measured delay exceeds the target delay, and assigns the op rate, which is the rate at which ops are submitted to the NIC, based on the more restrictive congestion window. Lastly, OneRMA provides support for encryption key rotation via Rekey op. Consider a OneRMA NIC in which a memory region is associated with an encryption key. Through Rekey, a remote key rotation service can directly change the encryption key without placing any trust on the local software stack and without involving local CPU. This ensures that only ops corresponding to the affected memory region fail, and importantly, the unavailability period can be reduced to a single RTT through Rekey. Having understood the main ideas of OneRMA, I will now go over the key results. It ensures that high priority applications are unaffected by failures or slowdowns of the low priority ones. OneRMA's congestion control converges to fair shares almost immediately, and reacting separately to local congestion leads to a 20x speedup. Native support for key rotation ensures minimal unavailability period during rotating keys, and all of this comes at a minimal cost of 0.5 cores to drive line rate, as OneRMA does congestion control and op management in software. In the interest of time, I will go into the details of the impact of OneRMA reacting to local congestion separately. We use one client and two servers, each connected by a 100 Gbps link. The client initiates a single long-running transfer with one server in the beginning and another one at around 400 microseconds. We repeat the experiment with and without reacting to local congestion separately. The x-axis plots the time and the y-axis plots the achieved submission rate. As we can see that without reacting to local congestion separately, convergence happens at around 1000 microseconds, while reacting to it separately, we observe a 20x faster increase in convergence. This is because OneRMA immediately detects local congestion as signaled by a sharp increase in the issue delay at around 400 microseconds. This is seen in the graph at the bottom, which plots the per op measured issue delay on the y-axis over time on x-axis. In conclusion, through experience, we find that existing RDMA technologies are ill-suited to multi-tenant data centers due to it being connection-oriented and having complex policies baked in hardware. And with OneRMA, we re-envision remote memory access for multi-tenant data centers. The OneRMA NIC is a simple connection-free and fixed function hardware with explicitly finite resources, and it aids software by providing fine-grained delay measurements and fast failure notifications. The OneRMA software implements congestion control and op management. Thank you very much for your attention, and I look forward to answering your questions.
All right. The first question is actually a bunch of questions are from Anna, and so I'm going to try to round robin. So the paper says memory regions for RMA use cases is typically proportional to tasks, not task pairs. Could you elaborate on that, please? Do you use different registrations to isolate, for example, different users' data? Arjun.
I see. It's a great question. So typically with respect to memory regions, what happens is that they are proportioned based on the users. And like if you take an example of
a distributed system, the typical pattern is that you essentially register the memory regions ahead of time based on like the number of clients and what they need, right? So it doesn't grow with like the number of endpoint pairs. So like the server essentially allocates the required memory regions and then clients access them. So it's not like a concern with respect to say other state like queue pairs in today's RDMA world, which essentially grow with endpoint pairs. That's what we meant by that. Does that make sense?
I think we should follow up on the channel, but let me go to the next question. I'm going to round robin. So a connectionless offload seems to trade off the performance of a hardware implemented connected transport for scalability and hardware simplicity, somewhat similarly to the trade-off of tightly versus loosely coupled systems. Do you see cases where you might still prefer connected offloads?
Okay, yeah, that's a great question again. With one RMA, we advocate going connectionless, right? And I would imagine that like a connection-oriented hardware transport would be still applicable in cases where like the workload is not large scale or it corresponds to like a few tenants or a small scale workload, because there you wouldn't go into the issue of your hardware connections being exhausted. So today RDMA offers like a connection-oriented hardware transport in some sense, but the issue there is connections can get exhausted between multiple tenant scale at which large-scale data centers operate on. But if your setting is such that there are only a few tenants or at a smaller scale, then you could possibly leverage a connection-oriented hardware transport.
Okay, great. So several of RDMA's benefits come from offloading tasks to hardware, example segmentation, but one RMA moves some of these back to software. Is there a fundamental sweet spot for the division of labor, or does it depend on the workloads and use cases and keeps evolving?
Yes, that's again a great question. So with one RMA, what we essentially do is that we do the division of responsibility in a different manner in comparison to RDMA today. And one of the guiding principles which we use there is that things which require, which can be done solely in hardware, right? We do them in hardware, like solicitation or DMing the packet data when you want to send them out. But things like failure recovery or ordering, which at times require application intervention, it's better to do them in software. And something like congestion control is being done in software today because we want to have the ability to iterate and evolve the design over time, which enforces us to do segmentation in software to some extent, so that we can get a frequent congestion signals. So based on that, we do the division of responsibility. So in a nutshell, like if you responsibilities which require application involvement, we would ideally want them to be done in software. And things which can be done in hardware solely, we would put them in hardware. Yeah.
I see. This is great. What is the higher level API that one RMA provides? Is it still similar to verbs? Does it get us closer to application data units as alluded in Amin's talk? And I think that will be the final question here.
Yeah, so with one RMA, we do provide backward compatibility to applications which use, say, existing verb APIs. Like the paper provides more details with respect to software abstractions, which we build on top of one RMA to actually continue using a verb-like abstraction where you have completion queues and you have command queues and those semantics. Alternatively, new applications which are developed can actually directly use the, do not need to stick to the verb APIs, and they can use like the raw one RMA APIs which are provided as well.
Thank you. So let's start with Q&A on Zoom. So Weibai asked, one main benefit of RDMA is low CPU overhead. If we unload many RDMA features to software, this will increase the CPU utilization and increase the cost of the cloud. What is the CPU overhead? And do you think the software-based solution can still work at 400G?
Yeah, that's a good question. So as we mentioned in the talk, with one RMA, we do a division of responsibility, which is not in sync with what RDMA does today. And our evaluation shows that we are able to drive 100 Gbps using half a CPU core. And we believe that that is a trade-off which we are making in 1RMA, and that's acceptable. I want to elaborate a bit more on how we came up with this division of responsibilities, right? Like with RDMA, a lot of the complexity is baked in hardware, right? But given our work, and it's hard to argue which is the right division of labor, and I think it actually depends on the workload. Like if we circle back to our original requirement of supporting workloads in a multi-tenant environment, right? We see scenarios where we have hundreds to thousands of clients which come and go, and they can cause lots of transient transfers, right? And if you do any allow them to perform large transfers with hardware segmentation, which RDMA allows today, then what can happen is that it will not work well, because there are a lot of these clients which come and go, right? And the only thing which the hardware can do is send it to the network, right? But if you chunk it down into smaller pieces and then send it, and you have that ability, then you have the ability to actually react to such transients. So that was one of the reasons why we push segmentation up in software, and we were also able to iterate over like what is the chunk size which we would want to use in our deployment, right? And that's one part with respect to segmentation. And coming to failure recovery, loss recovery, and ordering, what we find for our use cases is that it's application dependent. Like some particular application, say it's a key value store, it would want to try a different replica in case of a failure and not try the same one. So that's one of the reasons why we decided that the other things such as ordering and failure recovery need to be in software.
Right. So I have two more related questions. So what's the maximum? You sort of bake in the congestion control, right? And other things into the low-level hardware. I want to know what the max. So there's a related question on Zoom. What's the maximum size of the solicitation window, and how long do you wait for an OB response in the case of a packet drop?
That's a great question. So the thing is, we typically size the solicitation window proportional to like the bandwidth delay product of the network fabric in which we are targeting, right? And we account for some jitter, so that because jitter is something which does happen in practice, right? And the question with respect to how long do we wait on like reservations are made, and how long do we wait unless we declare like an op is failed. Typically, we set these timeouts to be 4 to 5 times the RTT, and we make this decision because our congestion control is highly responsible, and it makes drops and congestion not that frequent.
Oh, yes, very good. One related question is, do you actually bake in the congestion control to the hardware, or is there any changing or evolving the congestion control?
Correct, yeah. So I would like to correct you there. So 1RMA does not bake congestion control in hardware. It actually lifts congestion control in software. So the delay-based congestion control runs in software, but it is assisted by hardware in terms of the rich feedback it gets with respect to failures and also hardware measured delays, right? The only thing which is there in hardware is the solicitation window. So that can be thought of similar to being to flow control in some sense, so that we can protect against sudden incasts, which are typical in our environments.
In a multi-tenant data center, do you actually isolate the solicitation window across different tenants or different applications? Or
No, we do not. So this is a solicitation window which is shared across all the ops which the NIC is servicing, and this actually ties back to how long would you let an op reserve some capacity in the solicitation window, right? With 1RMA, what we do is that we refund the solicitation window capacity really quickly. It's just 4 to 5 times the RTT. So head of line blocking or the other ops are not stalled because of that.
Great. So one final question. So when I was hearing your talk, you talked about delay-based congestion control, but the nature of our 1RMA, like sending ops and getting response, seems more like you can benefit from a credit-based congestion control, right? So I wonder, have you thought of any different ways in performing congestion control?
So we did try with like a congestion window based congestion, like a window-based congestion control, and then we have like a sort of a rate-based one where we take the congestion window and then do it. The credit-based flow congestion control is an interesting idea. We do apply it with respect to like the flow solicitation window aspect, where those can be thought of to be credits, and we are doing admission control based on that.
Right, that's can be thought of with an outstanding amount of credits.
Yeah.
Okay. Thank you for your great talk.